right. Good afternoon, everyone. Thank you so much for being here with us at the second Gale conference. My name is Erin Owens. I'll be the moderator for this session titled AI-Driven Solutions for Digital Library Collections. Before we begin, just a few housekeeping reminders. We do have a code of conduct for this conference. I'm putting a link in the chat to that code. We hope not, but if you experience any issues related to conduct, you can contact the email address that is there in the chat as well. The session is being recorded. You can enable captions by clicking the Show Captions button at the bottom of the screen. Your microphones are muted when we get to a Q&A period at the end. If you would prefer to be unmuted to ask your question, you can raise your hand and I can give you the ability to unmute. Now it's my pleasure to introduce our speakers. Dr. Bipasha Banerjee is an AI research scientist and assistant professor at Virginia Tech University Libraries and holds a PhD in computer science. Her research focuses on natural language processing, information retrieval, machine learning, and artificial intelligence, and she is passionate about developing AI-driven solutions for digital libraries. Jennifer Goyne is a product manager at Virginia Tech University Libraries with over 20 years of experience in IT, specializing in software engineering, database design, full stack development, and project management. Before joining Virginia Tech, she was a lead developer and database administrator at the University of Missouri's College of Education for 13 years. Please join me in welcoming Bipasha and Jennifer.
Thank you, Erin. To get started, again, I am Jennifer Goyne, and this is my colleague, Bipasha Banerjee. And Bipasha, if you could share the slides, we could get started.
Can you see my full screen of the slides?
I can. Great. Well, welcome, everyone. Good afternoon. Thank you for joining us. As you can see there, we're going to be giving a presentation on AI-driven solutions for digital library collections. So we have a lot to cover. So Bipasha, next slide. So as you can see, we have a full agenda today. We're going to give you a little bit of an introduction about the digital library platform. We're going to talk about some digital collections and some challenges that we've had, and also talk about our motivation to move to AI. So why now? And integrating AI into the digital library workflow, as well as future development and conclusions. Next slide, please. So a little introduction to ourselves. It's a digital library and preservation team. So we are housed in university libraries on the beautiful Virginia Tech campus. And we have a wide range of, our team is composed of a wide range of expertise between software engineers, digital preservation specialists, AI researchers, librarians, metadata experts. So a full team. We provide digital access and preservation policies for public access. So a little bit about our platform, and I will give a little note. Virginia Tech loves to use their acronyms. So a lot of times I will not say digital library platform, and I'll just say DLP. So as I go through the slides, sometimes I'll just use the acronyms. So let's start off with the DLP platform. So in 2019, we had an initial launch of our first platform. It was the International Archive of Women in Architecture, IAWA. See, I told you we like to use the acronyms. And it was a cooperative agreement between university libraries, the Art and Architecture Department, as well as Urban Studies. And this platform is still going strong today. So since 2019, we have built a number of different platforms, but it still was missing something. So in 2024, we built a new platform and started migrating some of the sites onto that platform. And we worked with a number of different departments and regional and community organizations to get collections into that platform. So what does our DLP look like? So it is comprised of infrastructure, services. I mentioned is comprised of a number of different people with skill sets and preservations and policy. But let's start with infrastructure. So what does it look like? So this is a full stack platform. It's developed in React. I believe it's version 18 and some loosely TypeScript. The platform is built on AWS services. So We have all of our assets in AWS S3 buckets, all our digital assets, and our data is contained in multiple regions. So we do that for preservation purposes. And we also have a fixity service that we're developing. Why? Because we want to check and make sure that our digital assets, none of the objects change over time. So this is a brief glimpse of what our infrastructure looks like. So in the DLP, we're supporting long-term preservation and access to the university digital assets. Over this last year, and actually the last couple of years, we had a steady stream of growth and continued ingestion of the collections since the 2024 development of this platform. But not only with the collections, we're also extending growth in areas where we haven't reached before. So comprehensive 3D and models and AI integration, so that we've had growth in many different areas. So next, I'm going to go through this diagram. There's a lot going on here, so I'm going to pick it apart so I can give you a full glimpse of the tools and components in the DLP. So first off, let's start with the serverless cloud native platform. So I touched on that a little bit, but the Virginia Tech Digital Library platform is built upon the AWS, Amazon Web Services, and it's a solution that supports preservation, management, and user access to digital assets from the Virginia Tech libraries. Next up, you'll see below that is AWS. So again, like I had mentioned, our service is built on top of AWS services. It's a mouthful. And we keep, as I had mentioned before, we keep our digital assets in AWS. We also have tiled data in AWS. And we also have the metadata for our archive and collection. Now, in AWS, they're stored in non-relational tables, which are DynamoDB tables. And the final thing that we rely on AWS and that we had ventured and worked on this last couple of years is using AWS Textract. Now, AWS Textract is a AI-powered system that allows you to read documents and images, and it returns text and data. So it's a full system. So we had used that for some of our collections that I'll mention after this. So continuing around this diagram, we have the International Image Interoperability Framework, and IIIF is what we like to call it. So the IIIF viewer it allows you to deliver images and audio-visual to serve it up on a platform. So in our platform, we use a Minerva viewer, or not a Minerva viewer, a Mirador viewer. So this viewer allows us to use image annotation and to compare images on the platform, so delivering images up to the user. So continuing through our diagram, let's talk about metadata standards. So for metadata standards, we rely on Dublin Core. So we don't use Dublin Core for everything, but some of the fields or some of the data that we do require are rights and right statements. We require that and it has to be populated for each of our collection and archive items in the platform. Now, Dublin Core is pretty extensive, so we don't use all the metadata, but we do require a good bit of Dublin Core metadata in our system. So continuing through our diagram here, we have Meta Llama, and I'm not going to dive too deeply into that because I know Bipasha is going to touch on that a bit, other than it's a large language model. So continuing through our diagram, let's talk a little bit about 3D models, which is another component or tool that we have in the DLP. So within the last couple of years, we started using or providing collections more in a 3D format. And we wanted to do this to increase user experience and engagement with our collections. For example, we had a collection with the entomology department where we provided 2D and 3D images for viewing purposes. But also we are working with the Virginia Maryland College of Veterinary Medicine, where we're providing 3D models of equine teeth, or they call them clackers, and they're going to use that as a teaching tool for students. So we're really leaning into 3D models to provide on the platform. And then continuing through our diagram is batch tools. So there's a number of batch tools that we've written for the platform, and we've written them in Python, and we provide those out in GitHub repositories to be publicly accessible. But we've written these to help us ingest collections from our library network drives to move data up to our Amazon S3 environments or S3 buckets. And then the final circle that we didn't talk about, sorry, we're jumping ahead, is again, the acronym OAI-PMH. So most people know, if you don't know, OAI-PMH is Open Archives Initiative Protocol for Metadata Harvesting. See, it seems a little bit easier just to say OAI-PMH. But basically, what we're going to start working on next is a metadata harvester for the digital library. So I know I went through these very quickly, but I just wanted to give you a glimpse of a lot of the tools that we have in place and or that we're working on within the DLP. Next slide, please. So we're going to be talking about digital collections. So when Bipasha and I sat down, we had to have a lot of things in place. The people in place, the structure in place, the infrastructure, and the data. The data was the key. So we wanted to look at the data and try to highlight collections that were unique enough that we can run AI tools with. And we came up with these 3 different collections or 3 different use cases. So they were handwritten letters, and this is our Silas Step collection, digitized maps, which is our Newman map collection, and scanned newspapers, which is from the Montgomery newspaper collection. So for the handwritten letters, it was a small collection. There was only 17 digital objects in this collection and 121 megabytes. So it's a small collection, but it's unique because it's all handwritten letters from 1863. So it was a Civil War soldier had written these letters back to his wife of ongoings that was going on during the Civil War. So again, a small collection, but it was unique that we wanted to try to run AI models on handwritten text. The next example or next use case that we looked at was digitized maps, and that was coming from the Newman map collection. So there's approximately 7,000 digital objects in this collection, and it's about 3.9 to 4 terabytes of data, plus or minus. And this has a wide range of data. So you have historical maps from the 1790s from New Orleans to newer maps of USGS maps to shaded relief. So it's a wide range of maps that vary in size, shape, etc. A final use case that we looked at in working with AI tools is the newspaper collection. So this was the number of objects was slightly more significant. So this one had 28,000 digital objects. The size was a little less, so it was only 372 gigabytes. But these were newspapers just from around the Southwest Virginia region, and they ranged from 1910 to around 1950s. So challenges that we had with the collections. So if you look to the right of the screen of the digitized map, the maps were very large. Some of them were very detailed. And when I say large files, some of these individual files were a gig in size. And that was a slight bit of a problem because some of the tools that we were using, AWS TextTrack, the file was too large to run through TextTrack to do a text extraction. So the size of the file was a challenge. Another challenge was hard to read handwriting. So as you can see there, in the left-hand side, we have a sample of the Silas Step collection. The handwriting, while it can extract, some of the variants on how somebody did their cursive penmanship maybe were a little bit liberal. Instead of saying a pen in hand, a pen in fun. So trying to have the AI model decipher what and how the penmanship was translating in text was a little bit of a challenge. The other challenge that we had was related to the third collection that I mentioned was newspaper. So newspaper is a lot different than handwritten, obviously, and from digital maps, as it has complex layouts. So it doesn't read left to right. You have blocks of text that you go along that doesn't follow an order. So an article that starts on this page, page 2, may be on a separate image, and it may be in a different location. So it has a really different layout than the other use cases that we looked at. This collection also had quite a number of faded images, which also caused problems when we were trying to extract the text and have the AI models work with them. So why did we want to do this? Why was our motivation? We wanted to make these historical documents searchable and readable. We wanted to have more engagement. And this is how we wanted to get AI involved with our process, because we wanted to use these AIs as a tool so that we can provide machine readable text to the user. So when you see the handwritten text, you could read along to see what was going on, what was the historical context about. So again, we wanted to improve the workflow. At this time, I'm going to hand this over to Bipasha, and she's going to go more in a deep dive of how we integrated AI into the DLP. Bipasha?
Thank you, Jennifer. So now we are going to move on to discussing how we are integrating AI, developing AI solutions to help with accessing content, digital content within the DLP. So before discussing the workflows and what we're doing, how we're doing them, I wanted to give a brief overview of AI and wanted to touch upon on what AI is. So artificial intelligence is an amalgamation of different methodologies, algorithms that help mimic human learning, language understanding, reasoning, problem solving. The figure on the right-hand side depicts what comprise artificial intelligence broadly. It comprises of machine learning, deep learning, natural language processing, information retrieval, computer vision, and the most popular generative AI. Although AI, especially generative AI, has gained popularity, especially since the advent of ChatGPT in late 2022, the concepts have been in development for the last 7 decades. The earliest concept of an intelligent model can be traced back to the development of the Turing machine by Alan Turing back to the 1950s. Another definition that I wanted to kind of discuss was agents. We hear a lot in the media, articles, AI agent. What are these? So AI agents are inherently software technology. It's just software technology that have AI integration and are capable of making some intelligent decisions, which basically helps in automating tasks. We are developing AI agents within our DLP for text extraction and summarization, and these 2 tasks first before moving on to other AI downstream services that we want to work on. So in this section, we are finally diving into the AI agents and how we are using it in our data-driven environment. So we start with a collection item. The collection item is then passed through Textract, AWS Textract, which is the text extraction technology. Textract gives us line and word information. I'll be going into depth in subsequent slides, each of those subparts that I discussed. So once we have the line and the word information extracted, AWS Textract also gives us a confidence. So before we move on to using this extracted text in any way, shape, or form, we have to make sure that this is good enough. So error detection and correction is a module that comes next. Based on the confidence that the model generated, we bin those extracted text, and based on those confidences and low confidence words are then sent to human in the loop, sort of a platform where humans help in correcting those words. Again, I'll discuss this in detail in subsequent slides, so it'll make more sense. But once we have a confirmation that this particular word is the one that should be in this context of that line, we send the entire clean page text through the summarization module, which is a generative AI in this case, and we use Meta's Llama 3.2, 8 billion model. And finally, the figure on the right towards the right-hand side, we can see that we show the user the extracted text as well as the generated summaries. So the extracted text is meant to help user easily browse and navigate to their portion of content from this entire digital library collection that we have. It's very difficult to find what you're looking for. If you know the keywords, you can at least search on that extracted text and find that exact portion of the letter, for example, where the phrase was discussed. Similarly, summaries help users understand the content in a much summarized form, which is basically for the silent step letters, as Jennifer mentioned. It will help users um, understand what was written in the Civil War era, which is more adapted to modern times. So the English slightly differs the way people used to write, the way we communicate. So more adapted to modern times. So I'm going into depth about the AI workflows. Again, I wanted to highlight that our current workflow is meant to be AI aided, which means the main goal of this workflow is to leverage advances in AI, but also use humans' discerning capabilities. And that's like a combination that we want to use to help accelerate the processing times. Instead of, we're just trying to help make sure that we get as good of scores, as good results, good metadata, but we won't take as long as it traditionally would take. So stakeholders and our patrons are provided with better access to the material content through extracted text and the summary. So now we move on to the text extraction part of it. As I mentioned earlier, we are using AWS Textract as the text extraction tool. So Textract gives us the block type, which can be line, word, confidence of that, and the text that was extracted, along with other information such as IDs, the bounding box. So we save all these information in a DynamoDB as the JSON. So we make sure to preserve every step of the way. And then we also keep all the information such as confidence scores and bounding boxes, which will be used in later parts of this presentation and will be discussed. So again, we wanted to make sure that the text is good. And while analyzing the text, we did find some interesting results. So as I mentioned, AWS Textract will extract line as well as word. These are two different examples of the line text that was extracted. As you can see, the confidence of the line text was pretty high, 89% and 90%, but we do clearly see two errors. May was extracted incorrectly with a spelling mistake, as well as in the sentence, dear wife of now take my pen in fund to, it's clearly, it should be hand. There's also a preposition error over here. So it is important to have a look at both the line and the word information. For that particular line, the confidence was really high, but when we looked at individual words, we found that the confidence was low. So when we are binning those based on the confidence, we're also looking at the word level and not just at the line level, because we want to make sure that the words are inherently correct. So in this case, what we have done for the error correction pipeline is the words that ended up having low confidence were sent to a error correction pipeline where we've used language models to help correct the errors. So what we did here is, for that particular sentence, the word that had low probability was fund, which should have been hand. So we masked that word and sent this whole sentence to a language model, BERT in this case. So this is different from large language model. These are models that are attention, it were developed on attention mechanism, but they're not as large as LLMs. They are not generative in nature. They were designed to predict the next probable word in a sentence from their training knowledge. So that's exactly what we've used these models for. So given that we don't know what this word is supposed to be, what are the top probable words that should be here based on its inherent pre-trained knowledge? We see that hand was the top probable word that was generated along with order and other token strings. Now, what we did is we took the top 3 from this probability list and sent that over to a human in the loop. And so users are displayed with the top probabilities. And what happens here is it reduces the annotation time taken for someone to go and correct all the mistakes, and we are pointing to the mistakes and helping or asking help from human annotators to correct the pipeline. For summarization, we have used openly available LLMs, specifically Meta's Llama 3.2. One thing that was really important to us was being able to use LLMs that did not have paywall and is free for academic research, which Llama is. This is because we wanted to have the control over having the model weights and the control over how much the model generates versus hallucinates. So we wanted to interact with the model programmatically and not just through APIs. So we do run it on our own servers here at the university library. The generated summary is intended to help users comprehend the content within each of the collections better. So this is an example, the figure on the right-hand side, one of the letters that were passed through the extraction module, correction module, and then it was sent to the summarizer, and this is what the summary was for that letter. So now we move on to some future development and conclusion from what we have learned so far. Some future work involves, and I have been currently investigating this, is using openly available models for text extraction. So as you may recall, text extraction is currently using AWS TextRack, which is a proprietary model. Now, it's been shown to do pretty well, but it's, again, you have to pay for accessing their APIs. And the biggest challenge that I found with TextRack is they don't give us access to their model weights, which means we don't have any control. We cannot fine tune their model. We're basically bound by their APIs. So to move away from that, we are looking at using other OCR technologies to extract the text using either LLMs or even machine learning. And that also gives us more control and with our own homegrown technologies, which are contained within our servers. So privacy and ethical, all the data concerns that we have would be somewhat mitigated because we are not sharing that data with AWS or any other company. The second thing that we are working towards is scaling up the error correction pipeline and incorporating that within our UI. So the DLP has a web-facing UI, which the public accesses. So at this point, the error correction pipeline is something that's internal. So we want to open up and see if we can get more public, like point out to these, what are the errors that they find, give us feedback. And make it truly a human in the loop pipeline, because then that could be used to train models in the future, but that's something we haven't yet touched. It's something that we want to do in the future. One more interesting thing that I wanted to talk about, and this pertains specifically to the map data. So from the USGS maps that we have, we call it human maps. These are all digitized topographical maps. What we want to do is not just extract the information that's within the map, but also extract information from the borders of the map, because they contain a lot of useful information that if we can extract and classify would aid in creating the metadata and make the whole process go a little bit faster than the traditional methods. Now, the map data inherently had issues, and that's something that we're working towards. So they're huge, they're very large files. So we had to break the files into smaller tiles and smaller pieces and work on each piece at a time, which, yes, makes it computationally a bit more expensive, but that's the best way we could handle maps. Within maps, the other problem that arises is the text is not always horizontal. It could be at an angle. For example, you see the branch is completely at an angle. The way we mitigated this was to extract text at different angles from one particular clip, and we were able to successfully extract the text within the map. We were also able to get text from within the borders of the map, and we subsequently want to classify them into its proper classification label. For example, United States should be a country, and it could also be a location. So that is something that we're working towards. So in conclusion, we are trying to improve access to digital content, especially at the granular level, to help with improved understanding of content that's within each collection items. So instead of just showing users our pictures, we want to give them more access through the extracted text to able to search and navigate to their portion of interest easily. This also helps us further our text analysis and help with digital preservation. We want to learn more from the past, so we can use all of those data that we extract and gain more insights from those extracted texts. It also improves user engagement with the platform. Since we are giving access to more granular level information, we are hoping it will be more intuitive and exciting for our users to engage with the content within our collection. And finally, I wanted to touch upon the benefits of using LLMs. So again, we are trying to augment humans' discerning capabilities with machines' ability to deal with large amount of data, to work on complex natural language processing tasks. We want to move towards only using open for research LLMs because we want to have more control over model weights, be able to fine-tune models as and when needed. At this point, we're working only with smaller version of LLMs on a cost-effective hardware. So LLMs need something called a graphical processing unit or GPUs, which can get very expensive if you want to run a huge large language model on them. So we have been able to use the smaller versions and get decent results using them, and make it doable on a university like academic library to be able to handle such complex NLP tasks. So that was it. I would like to thank our dean, Dr. Tyler Walters, our associate dean for IT, Bill Ingram, our colleagues at the library who have helped us get access to these collections, maps, etc. The software team at the DLP, as well as AWS for their continued support when we were working with those collections. These are our references, and thank you. We'll be happy to answer any questions.
Fantastic. Thank you, Jennifer and Bipasha. If anyone has questions or comments, please feel free to put them in the chat box or the Q&A box. If you'd prefer to ask your question aloud, please just raise your hand and I will give you the ability to unmute. Not seeing any questions yet. Oh, here we go. Cynthia asks, is AWS very costly?
Jennifer, did you want to take that?
Sure, I can take that one. So is AWS costly? It depends. So a small collection like the Silas step, there was only 17 digital objects. There were 17 letters in that collection. It was like a fraction of amount of money. I want to say it was like $2 or something. It was such a minuscule amount of money to run because it's like pennies on the dollar. But when you have a larger collection, then it adds up. And if you have a large collection and you haven't done any processing, like pull out the data that has just images and no text, you will still get charged for that. So again, it depends on the collection. Some of them you may have to do some pre-processing. And I think they have their pricing on the website, but it can get costly. Bipasha, would you like to add anything to that?
Yes, from my experience, textract specifically, if you're just dealing with very small files, simple files, it won't be as costly. But again, with the map collection, map, like each map was such like large, it was huge. So first, it wasn't able to process. If you would have to like batch it into different smaller batches, it might be able to process, but then you wouldn't have the continuity of the extracted text. So there's a lot of issues when dealing with different kinds of collections, but textract in itself, if you're dealing with small data, wouldn't be as costly. But I think the question is, is AWS very costly? Depending on what service you're using, if you end up using a Gen AI through their SageMaker, it can rack up $8,000. You don't know how it's what resource it's allocating, what GPU it's allocating. So depending on those factors also, it can get way out of hand very quickly.
Excellent. Let's see, Gregory asks, with metadata description of, say, a photograph collection, what percentage of that is done without human intervention? In our case, so much of it requires institutional knowledge of local places and people.
That's a great question. So we have another collection which we did not mention over here because this is an open question we are also kind of trying to figure out an answer to. We have some yearbooks which has photographs. With the photographic collection, I have used images and LLMs. The LLMs are able to explain the image, but again, it won't have very like specific domain or area specific answers where human intervention is almost necessary. So at that point, we were kind of weighing, is it worth kind of explaining what the AI, what the picture is talking about, or is it worth like directly sending it to a human? But yeah, that's something because a model won't have that kind of knowledge. It's like pros and cons of using models.
Right, I can see how it could help you get the more generic level, and then you'd send it to a human that would do that much more contextual, local level. Yeah. Kevin just commented that he really appreciates the long-term planning and accessibility of the objects being digitized. Gregory says, thanks. It's hard explaining to higher powers why AI can't describe everything. Have you, have you found that you've faced any issues in terms of communicating to administrators or other stakeholders about this use of AI? Have you gotten any kind of pushback or questions or anything?
So I wouldn't say like pushback. I think Virginia Tech in itself is very supportive in our endeavors, so we haven't faced that. But since starting, I have had like conversations with different colleagues from different perspectives, which I think is extremely important to have those conversations because, for example, certain areas you have to be 100% correct. There is no room for error. If it's medicine, if it's clinical trial, there is no room for error. So I do appreciate those conversations. And again, there are ways of handling with like using AI without like hallucination is a big problem. Yes, but there are ways of handling it programmatically. There are hyperparameters that you can control. And not everything needs AI intervention. Sometimes a statistical model that was developed in the 70s will do a great job at that particular task. So I think I've had those conversations, but we haven't faced pushback. It's more so colleagues trying to understand, okay, I want to use it in my context. How do I do that?
Gotcha. That's great. That's great. If anyone's got any other questions, feel free to enter them. Here we go. Cynthia asks, how can we get a copy of your slides? I will say that we are going to invite all of the Gale presenters to share their slides if they would like to. And then any slides that are shared with us will be uploading to an open repository on OSF. And Bipasha has also included her email address there in the chat. Right. Any other questions? Feel free to pop them in the chat box or raise your hand if you'd like to be unmuted. Jenny says she's very excited about your work.
Thank you.
And our contact information is also attached at the last slide of our presentation. So if you didn't copy down Bipasha's email or you want to get in touch with me, here's our contact information.
Excellent. Right. Well, that was fantastic. Thank you both. If there are no more questions, then I will wrap this up. Say thank you for presenting. Thank you, everyone, for attending. And I hope everyone enjoys the rest of our Gale conference.
Thank you, Erin.
Thank you, Erin.